When an acid and base are mixed together, they neutralize each other. Shown here is a reaction between an acid and a base undergoing an acid-base neutralization reaction. Let's look at how it happens. The acid is going to give up its proton. The base is going to take it. So the proton here is going to be joining up with the hydroxide there. What does that make? Two hydrogens and an oxygen makes water. What's left over? The hydroxide and the proton went to make water. What's left over is sodium and chloride. Sodium chloride. A salt is actually defined as the product of an acid-base neutralization reaction. But why is it that this works out this well? Well, acids are formulas that are nonmetals attached to hydrogen, hydrogen with a nonmetal. Bases are metal hydroxides. So when you go to mix them together, the acid proton jumps onto the hydroxide to make water. What's left is a metal with a nonmetal, which is a salt. Buffers are solutions that stabilize pH. So you add a little bit of acid or a little bit of base and the pH remains essentially the same. To make a buffer, we can mix a weak acid with the salt of its conjugate base. And the reason is that this works is that you have both acid and base in there. Let's look at this in a little bit more detail. Here is a buffer system that you can make by adding roughly equal amounts of acetic acid and something that would provide its conjugate base, like sodium acetate. So I would mix equal quantities of these two in water, and then I would have a large amount of the weak acid and a large amount of the conjugate base. If I add acid to the system, I cause this to increase. There's so much of this available that the increase is consumed and the more acetic acid is made. So the equilibrium shifts to the left. However, the amount of acetate and the amount of weak acid is so large that when I'm adding a small amount of acid, I don't change the percentages of these much. So my proton concentration reverts to what it had been before I added acid. Likewise, if I add base to the system, I'd remove hydronium ion. That would shift the equilibrium to the right, but the large quantity of the weak acid and the large quantity of this would cause the equilibrium shift to not change the percentage of the acetic acid much. So this concentration remains stable. We have a special buffer system in your blood due to high levels of carbon dioxide. This is the principal way that your body controls pH. There's some other ways, for instance, through proteins, buffering, and in your cells, phosphate buffers. But in your bloodstream, this is the most important buffer system. You need to pay close attention to this if you're going into nursing. Carbon dioxide is produced in huge quantities by your muscles and other metabolic processes. As soon as it's formed, there is an enzyme that will cause it to change into carbonic acid, and then carbonic acid rapidly will dissociate to protons and carbon dioxide. We can actually skip this intermediate and just look at the equilibrium between carbon dioxide and water and protons and bicarbonate. The amount of carbon dioxide, therefore, controls the pH of your blood. You actually control your pH by your breathing. When your carbon dioxide level gets high in your bloodstream, there's a sensor in your body that detects that proton concentration is increasing. your pH is decreasing. So in response, it triggers your lungs to breathe harder so that you can expel the carbon dioxide. If your carbon dioxide levels drop, let's say due to inactivity, your proton concentration is going to drop, and the sensor then triggers your lungs to breathe more slowly. However, this can get messed up. Let's look at an example. You have something called respiratory acidosis that comes from respiratory problems. An example would be you're given a drug that slows your breathing. If you slow your breathing, your carbon dioxide levels are going to build up. If your carbon dioxide levels build up, what happens? You're going to make more protons and more bicarbonate. The proton concentration goes up, and you're going to get an acidic pH in your bloodstream, which can be dangerous. So there are problems, there are things that can cause respiratory acidosis, and it's all caused by your respiratory system not expelling enough carbon dioxide. If you have respiratory alkalosis, what's happening there is you are putting out too much carbon dioxide. If you hyperventilate, you expel too much carbon dioxide, and so you can be throwing out your carbon dioxide, and what happens? You're going to have a shift in this reaction to the left. As a result, your proton concentration will go down and your bicarbonate concentration will go down. So what happens when you are in a situation where you breathe too hard, or there's something else that can be causing you to expel too much carbon dioxide? What happens is your pH goes up and your proton concentration goes down. Now, to finalize this, we're going to go back to determining concentrations of proton hydroxide and pH. And in order to help you see this a little bit better, I'm going to do this with an acidic solution and a basic solution side by side. So we're going to look at the same concentrations of hydrochloric acid and sodium hydroxide. When hydrochloric acid dissociates, we get protons. When sodium hydroxide dissociates, we get hydroxide. So in the acidic solution, I have 0.03 molar of protons. In the basic solution, though, I have 0.03 molar of hydroxide. We're going to make a table to go through the concentrations and how they compare. So with sodium hydroxide, I have my hydroxide concentration as 0.03, but with hydrochloric acid, the proton concentration is 0.03. I can figure out my proton concentration and my hydroxide concentration from the water dissociation constant, that hydrogen ions times hydroxide ions gives you 1 times 10 to the minus 14. But they're rearranged differently because here I'm figuring out my proton concentration. Here I'm figuring out my hydroxide concentration. I plug 0.03 in and I get that number. Here I plug 0.03 in and I get that number. You see how everything's opposite depending on whether it's a base or an acid? Now I go to figure out my pH. pH is proton concentration. So I need to take my negative log of this number for sodium hydroxide, but this number for hydrochloric acid. So my pH for the sodium hydroxide solution is the negative log of this, which is 12.5, and my pH for the hydrochloric acid solution is 1.5, because the negative log of this gives you 1.5.